In this presentation, I'll go through some notes from Chapter 12 of book Designing Data-Intensive Applications. Chapter 12 is called The Future of Data Systems. This chapter discussed new approaches to designing data systems and included author's personal opinions and speculations about the future. He started with the observation that there's no one single tool that can efficiently serve all possible use cases. It's no surprise. So applications necessarily need to compose several different pieces of software to accomplish their goals. Again, there should not be a surprise to that. He discussed how to solve this data integration problem by using batch processing and event streams to let data changes flow between different systems. In this approach, several systems are designated as systems of record and other data is derived from them through transformations. This way, we can maintain indexes, materialize views, machine learning models, statistical summaries, and more. By making these derivations and transformations asynchronous and loosely coupled, a problem in one area is prevented from spreading to unrelated parts of the system, increasing the robustness and fault tolerance of the system as a whole. Expressing data flows as transformations from one data set to another also helps evolve applications. If you want to change one of the processing steps, for example, to change the structure of an index or cache, you can just return the new transformation code on the whole input data set in order to redrive the output. Similarly, if something goes wrong, you can fix the code and reprocess the data in order to recover. These processes are quite similar to what databases already do internally, so we can recast the idea of data flow applications as unbundling the components of a database and building an application by composing these loosely coupled components. Derived dataset can be updated by observing changes in the underlying data. Moreover, the derived state itself can further be observed by the downstream consumers. We can take this data flow all the way through to the end user device that is displaying the data, and thus build user interfaces that dynamically update to reflect data changes and continue to work offline. Next, we discussed how to ensure that all processing remains correct in presence of faults. We saw that the strong integrity guarantees can be implemented scalably with asynchronous event processing by using end-to-end operation identifiers to make operations idempotent and by checking constraints asynchronously. Clients can either wait until the check has passed or go ahead without waiting but risk having to apologize for a constraint violation. This approach is much more scalable and robust than traditional approach of using distributed transactions and fits with how many business processes work in practice. By structuring applications around data flow and checking constraints asynchronously, we can avoid most coordination and create systems that maintain integrity but still performs well even in geographically distributed scenarios and in the presence of faults. We then talked a little bit about using audits to verify the integrity of data and detect corruption. Finally, we took a step back and examined some ethical aspects of building data-intensive applications. We saw that although data can be used to do good, it can also be used to do significant harm, making justifying decisions that seriously affects people's lives and are difficult to appeal against, leading to discrimination and exploitation, normalizing surveillance, and exposing intimate information. We also run the risk of data breaches, and we may find that a well-intentioned use of data has unintended consequences. As software and data are having such a large impact on the world, we engineers must remember that we carry a responsibility to work towards the kind of world we want to live in, a world that treats people with humanity and respect. I hope that we can work together toward that goal. Here are some of the highlights: unifying streaming and batch processing. The ability to replay historical events through the same processing engine that handles the stream of recent events, for example, log-based message brokers, have the ability to replay messages, and some stream processor can read input from a distributed file systems like HDFS. Exactly one semantics for stream processors, that is, ensuring that the output is the same as if no faults had occurred, even if faults did in fact occur. Like with batch processing, this requires discarding the partial output of any failed tasks. Tools for windowing by event time, not by processing time. Since processing time is meaningless when reprocessing historical events, for example, Apache Beam provides an API for expressing such components, which can be run using Apache Flink or Google Cloud Dataflow. Just because an application uses a data system that provides comparatively strong safety properties such as serializable transaction, that does not mean the application is guaranteed to be free from data loss or corruption. For example, if an application has a bug that causes it to write incorrect data or delete data from a database, serializable transactions aren't going to save you. It is worth taking seriously. Application bugs occur, people make mistakes, and although immutability is useful, it is not a cure-all by itself. And continuing with the end-to-end argument for databases, the scenarios for suppressing duplicate transaction is just one example of a more general principle called the end-to-end argument, which was articulated by Salzer, Reeds, and Clark in 1984. The function in question can completely and correctly be implemented only with the knowledge and help of applications standing at the endpoints of communication system. Therefore, providing that question function as a feature of the communication system itself is not possible. Sometimes an incomplete version of the function provided by the communication system may be useful as a performance enhancement. In our example, the function in question was duplicate suppression. We saw that TCP suppresses duplicate packets at the TCP connection level. Some stream processors provide so-called exactly one semantics at the message processing level, but that is not enough to prevent a user from submitting duplicate request if one of the request times out. By themselves, TCP database transaction and stream processors cannot entirely rule out duplicates. Solving the problem requires an end-to-end solution, a transaction identifier that is passed all the way from end user client to the database. The end-to-end argument also applies to checking the integrity of data. Checksums built into Ethernet, TCP, TLS can detect corruption of packets in the network, but they cannot detect corruption due to bugs in the software at the sending and receiving ends of the network connection, or corruption on the disk where the data is stored. If you want to catch all possible sources of data corruption, you also need to have end-to-end checksum. A similar argument applies with encryption. The password on your home Wi-Fi protects against people snooping your Wi-Fi traffic, but not against attackers elsewhere on the internet. Although the low-level features, TCP duplicate suppression, Ethernet checksums, Wi-Fi encryption, cannot provide the design end-to-end features by themselves, they are still helpful since they reduce the probability of problems at the higher levels. For example, HTTP requests would often get mangled if we didn't have TCP putting the packets back in the right order. We just need to remember that the low-level reliability features are not by themselves sufficient to ensure end-to-end correctness. Applying the end-to-end thinking in data systems. This brings me back to the original thesis. Just because an application uses the data system that provides comparatively strong safety properties such as serializable transactions, that does not mean the application is guaranteed to be free from data loss or corruption. The application itself needs to take end-to-end measures such as duplicate suppression as well. This is a shame because fault tolerance mechanisms are hard to get right. Low-level reliability mechanisms such as those in TCP work quite well, and so the remaining higher order faults occur fairly rarely. It would be really nice to wrap up the remaining high-level fault tolerance machinery in an abstraction so the application code need not worry about it. But again, the author fear that we have not yet found the right abstraction. Timeliness and integrity. Timeliness means ensuring the users observe the system in an up-to-date state. Integrity means absence of corruption, no loss, no contradictory or false data. In particular, if some derived data set is maintained as a view onto some underlying data, the derivation must be correct. For example, a database index must correctly reflect the components of a database. An index in which some records are missing is not very useful. Just as the Industrial Revolution had a dark side that needed to be managed, our transition to the information age has a major problem we need to confront and solve. I believe that the collection and use of data is one of such problems. In the words of Bruce Schneier, data is the pollution problem of the information age, and the protecting privacy is the environmental challenge. Almost all computer-produced information, it stays around festering. How we deal with it, how we contain it, and how we dispose of it, it is a central health of information economy. Just as we look back today at the early decades of industrial age and wonder how our ancestors could have ignored pollution in their rush to build an industrial world, our grandchildren will look back at us during these early decades of the information age and judge us on how we address the challenge of data collection and misuse. We should try to make them proud. This concludes Chapter 12 notes and the book. Hope this was useful. Have a nice time. Like and subscribe for more such content.